Hello, and welcome to today's session, Behind the Headlines, the Prima Implant and What It Means for You. I'm your host, Matthew Levine. I'm the Director of Grants Advocacy and Partnerships at the American Macular Degeneration Foundation, and I'll be guiding our discussion today. You should also know that we're joined by my colleague, Jennifer Williams. She's our Director of Communications and Community Outreach, and she'll be watching the chat should you have any questions as they post, and she'll be helping people with technical issues. So you can chat with her if you're having a problem. Our goal today is to get behind the headlines and unpack what this news actually means for you. So we want to understand what the research means, what it doesn't mean, and how you can make sense of this development when you see it in future news. And as we do so, we hope that you'll not only learn about the Prima implant, but how to read research news in general with a kind of a critical eye, not a cynical eye, a critical eye, so that you can ask the right questions of your eye care providers. Today's program, by the way, is going to be available in a few days for download or watching at macular.org and also on the AMDF YouTube channel. And during the program, if you have questions, you can post them in the chat area. We'll do our best to get to them, but I got to tell you, we received a lot of questions already, and we're going to try and get to as many as possible. So let's get started. Today, we're fortunate to be joined by Daniel Palanker. He's a PhD, professor of ophthalmology at Stanford University, and he's co-senior author of the paper that's drawn so much attention. I'm sure that's why you're all here. It really made a lot of splash in the news. So Daniel, welcome. And before we dive in, can you just tell us briefly about your areas of expertise and also describe your role in the development of Prima and maybe even of the clinical trials?
Thank you. Hello, everyone. Thank you for the opportunity to explain what Prima is. And the Prima is a photovoltaic retinal implant. It's developed by our group at Stanford since 2004. Was then commercialized by Pixium Vision. It's a French startup company starting in 2013 until it was acquired by Science Corporation, which is an American startup company, last year. So I'm a physicist by training. I work at the interface of physics and medicine, primarily in ophthalmic applications, such as ophthalmic lasers, electronics, and imaging systems. I'm professor of ophthalmology and also by courtesy of electrical engineering at Stanford University. Should I explain how the system works?
Yes, sure. Let's just get right into it.
Yeah. So I presume you can see the image on your screen, which shows on the left normal diagram of healthy retina. It is composed of, roughly speaking, three layers: photoreceptors at the bottom that convert light into neural signals. Then in the middle, there is a layer of primarily bipolar cells. It's neurons that process the signals from photoreceptors and deliver them to output layer of the retina called ganglion cells that convert the signals into spikes. So make them binary, basically, signal. And in language of electronics, you can call them digital cells. And this cells send signals encoded in action potentials into the brain through optic nerve. In retinal degeneration, we lose photoreceptors. And our approach is to replace these lost photoreceptors with an array of photodiodes shown on the right. These photodiodes convert light that reaches the retina into electrical current. Current flows between electrodes and these pixels through the tissue, polarizing nearby cells. The cells that are polarized in electric field change their potential. And basically, this replicates the effect of photoreceptors in a sense that transmit visual information to bipolar cells, affecting their potential. And the output of these cells then goes through the retinal neural network to ganglion cells and to the brain. So basically, we substitute only one layer of cells in retina, the photoreceptors, and we rely on the rest of the retina doing its job of signal encoding. I think that's the fact that we approach this restoration of sight this way preserving in retinal signal processing is essential part of our success. Other groups try to stimulate output cascade of the retina and fail to produce more than just light sensitivity, not the form vision that we observe in our patients.
That's the next question I really wanted to ask you. When this story hit, it was such big news. News outlets everywhere were talking about this, but it was hard to get an actual description of the kind of vision that people experience when the implant is in. So, can you talk a little bit about the kind of vision that you're experiencing, and maybe a little bit about its safety, because obviously it's a
Yeah.
surgical thing.
So maybe a few more details of what patients actually use. So implant is one side of the story, but implants convert light into electrical current to stimulate cells, and ambient light on the retina is just not enough for electrical stimulation of bipolar cells. Photoreceptors are very sensitive to light, and they amplify a signal, converting it photons to ions flow with a factor of up to 1 million, and photodiodes don't. So we have to use more intense light than ambient, and therefore our system includes glasses, augmented reality glasses that have camera image processing, and then we project this image after it's intensified into the eye using invisible wavelengths, near-infrared light, 880 nanometers. We use invisible wavelengths not to overwhelm the remaining photoreceptors in the periphery of the scotoma in HLH macular degeneration, where normal photoreceptors still do their job. So this invisible beam is more intense than ambient, and that is sufficiently intense to stimulate cells with this photovoltaic conversion of light into current. Photovoltaic is just like solar panels on a roof. They convert solar sunlight into electrical current. Here we convert light projected from the glasses into electrical current. And so patients wear these glasses. You can see here an image of a patient. This is not a patient, model demonstrating how these prototype glasses look like. And patients look into this display, and this is where they see an image, and it appears in black and white. So basically, the patients describe the color as whitish, yellowish, white, bluish, but white colors. It's monochromatic. And they see shapes. So we project lines, we project letters, words, text, and they see it as a form vision. And that, I think, is the most remarkable aspect of our success, is that it's basically like normal vision, even though it's black and white, not yet grayscale even, and not color certainly, but it is vision that allows them to read and write. And that's what they describe it as a bright patterns when we project bright patterns on a dark background.
As you were speaking, another thought just occurred to me. After this is implanted in your eye, do you feel it in the back of your eye, or?
No, you don't feel anything on the back of your eye. We don't have sensors there of, pressure and so on. It is held just by the retina. It is very thin. It is 30 micrometer thin, so it's a half of the thickness of the receptor. So my first picture, I think we try to keep it to scale. You can see that it's in thickness about half of the layer of photoreceptors, which are about 70 microns, and this is 30. So it's quite light, and it is held there. Patients don't feel its presence, except when they start activating it by augmented reality glasses.
Okay.
And the implant itself, you can see here in a higher magnification, is 2 by 2 millimeters. It is composed of 100 micrometer pixels. Each pixel is composed of two diodes connected between active and return electrodes. This little disc in the center is active electrode, and the mesh of hexagonal mesh around is returns. On the left, you see clinical picture of the fundus of a patient with an implant right in the middle. And at the bottom, you see side view where retina above, this dark layer above, the implant is actually the layer of cells we are targeting, bipolar cells. So as you can see, retina sits right above the implant, and then outside, it is reattached basically normally to the retinal pigment epithelium.
So I recall reading the study that this is a procedure that's been developed that most retina surgeons can perform. The procedure itself is clear and simple, and that it's safe. Um, can you discuss its safety a little bit?
Yes, so we conducted two studies. One was primarily safety study called feasibility trial with 5 patients in Paris, 2018, 2023. And then much larger study recently in 23-24 with 38 patients in 17 centers of 5 European countries. It was UK, France, Germany, Netherlands, and Italy. And in terms of safety, we monitor, side effects of surgery, but also preservation of the residual natural vision. And the residual vision was not affected by the implantation, which was very important because you don't want to damage whatever is left, even though the acuity is low, but it is still a normal vision that we want to retain, and that was demonstrated. And the reason we can do this safely because this implant is completely wireless. It has no wires attached, no power supply. It is activated by light. So it's just inserted under the retina and left there, and it's activated by light. So that now we have this implants on our first patients working more than 5 years. They're still working. Patients still have the same acuity. Visual acuity matches the pixel pitch, so the minimum features that you can resolve in a letter, like gap in the Landels in a letter C, for example, or bar widths in other letters, is 1 pixel. But using electronic zoom, patients can see much better. And so what we demonstrated in this pivotal trial, that patients would see using electronic zoom with 81% of patients improved acuity by more than 2 lines on this chart, and 78% improved more than 3 lines, and on average, the improvement was more than 5 lines. And that obviously, if you use electronic zoom, it comes on the account of reduced visual field, but it is still was, what patients preferred. They were allowed to control zoom to their, level of convenience. And if you want, I can show you a video of a patient reading the book, which is a photo here on the left, but we have a video of that if you'd like, or we can just stay here.
I just have a few more questions about this. So,
Go ahead. Yeah.
so obviously, the Prima doesn't just deliver vision as experienced. The person wearing it can modulate it a little bit. They can zoom in. Can
Yeah.
they also adjust other elements of vision, like the light and dark contrast?
Absolutely, yeah. So currently, the clinical trial was focused on reading, and that's a standard, assessment of vision by just vision chart, as shown here, how many letters you can read, how many lines, and therefore, currently, it's optimized for black and white image processing. So it's a maximum contrast, maximum brightness we can deliver. But next step, actually, what we are starting now with the same patients, is to assess their range of contrast sensitivity and optimize it for face recognition. For face recognition, binary representation is usually not enough. You want grayscale, and that's exactly what we are going to measure and optimize image processing for that. And also for other natural scenes. But face recognition is a second line in wish list of patients. Usually they want to read and they want to recognize faces as first two priorities. And so that's we delivered the first one. We now will be focusing on the second. And the other big improvement that we want to deliver is better resolution. We currently have a next generation implant that works in rats in my lab that has pixels 5 times smaller. Instead of 100 microns, there are 20 microns. And if this will be successfully working in human patients, it will provide acuity of 20/80, and we zoom down to 20/20.
Oh, okay. Um, I've got to ask you this question because I think some of the news articles got it wrong. Some of them stated that the study did not show that Prima improved quality of life. But when
Oh,
I read
yeah,
the study, it said that the study was actually not designed to measure quality of life.
right.
Uh, so, because look, I'm not a scientist, but it seems to me that if it gives you the ability to read, that's an improved quality of life.
Right. So the questions of quality of life are tricky one. It's a questionnaire, and it has to be powered enough to have enough people to address this in a quantitative way. The study was designed to just measure vision, visual acuity, and that's what we did. We reported that. It's very consistent, and the results are remarkable. But questionnaire about quality of life was like ad hoc, post-assessment, and few patients were invited to respond, and so it gave some kind of feeling of what patients basically do with this, how they use it at home, and they responded that some read, they play cards, they fill crossword puzzles, some use it for cooking, but there was no like easy way to quantify it with a few patients that were asked. So next, maybe studies will be more quantitative about quality of life improvement and will demonstrate something, quantifiable. But currently, it was more of how it is used at home.
Okay. So there have been other retina implants in the past. I recall one called the Argus 2,
That's right.
and that was actually being put into people. But I guess the company that supplied it went out of business.
Right.
What separates Prima from all these previous attempts
Yeah.
to do?
So there are basically uh, two, approaches to retinal prosthetics. One is called epiretinal, where you put the implant on top of ganglion cells and stimulate ganglion cells, and that was Argus 2. And in that case, you have to encode information in a binary patterns of spiking, and that's very difficult because many cells in parallel process different aspects of the image and use different codes to deliver it to the brain. Because this was not respected, it was stimulating indiscriminately many cell types, patients basically saw just light, not a form vision. And by scanning, you can see where the source of light is coming from and find line on the floor, for example, to follow a way or doorway. But it wasn't good enough to replace, a white cane or guide dog. And therefore, it failed to, you know, uh, provide sufficient improvement, which is worth a surgery and uh, associated risks. And so device didn't gain popularity and was abandoned. And company went basically with this product out of business. They actually tried to recycle this implant and place it in the brain as a cochlear implant, but that didn't produce useful results either. So I think that was not approved, and I'm not sure if they're seeking approval of cortical implant or not. Um, there were other implants, retinal implants, maybe the best known is subretinal implant called Alpha AMS or AMS from Germany, company in Tübingen called Retina Implant AG. Their performance wasn't as impressive as ours, but still there were some patients that could recognize patterns. But their implant failed. It had power supply behind the ear and cable going under the skin into the eye and into the implant. And over a few months, this implant stopped working and basically broke down, and they had to be explanted. So the company also went out of business in 2019. And this was an implant approved in Europe, not in US. Argus 2 was approved in US as well. But both of them basically failed. So our implant doesn't have any cables, and our implant is placed in subretinal space and utilizes retinal neural network to provide retain as many features of natural signal processing as possible. And we see indeed a lot of features of normal image processing preserved when we study the prosthetic visual code versus normal. And indeed, our patients see form vision. Moreover, they see it simultaneously with normal peripheral vision. So if you show a line that they can resolve in the periphery, say wide green lines, they see it. Then in the center, it becomes white, and then it green again. And it means that basically it merges prosthetic central vision with residual low resolution peripheral vision.
How is that working? How does that work in the brain?
Yeah,
How is it
that's
possible?
remarkable that we deliver code which is not exactly natural. It has features of natural retinal code, but it's certainly not perfectly the same. But it is close enough for the brain to recognize it as a visual code and decode it as an image. And that's remarkable. I was very pleased to see that this is possible. There is analogy to that in the world of cochlear implants. Cochlear implants started as a replacement of hearing for completely deaf people, but later they um, now being used to provide only part of the missing frequency range, high pitch, while low frequencies are still perceived naturally. And patients learn to utilize simultaneously the residual natural hearing and prosthetic. It's not easy, it takes time, but brain can do that. And so what we do with our implant is similar in a sense that central vision is prosthetic, peripheral is natural, and brain can merge them.
Can you describe how long it actually takes for someone getting this implant, starting from the point where they have the surgery, recovery from the surgery, training, and then, as I understand it, there's a period of time where the brain learns there's some kind of improvement over time. How long from surgery till you're really experiencing the best vision that the device can give you?
We have now 43, 45 patients. So we see that there is a spectrum of abilities. Some patients get it right from the very beginning, and some take time to improve. And we see on average there is improvement between 6 months and 12 months measurements, for example. And when we ask patients what is improving, some of them say that they see initially an image as a bit noisy or lines as a bit curvy, not straight. And over time, the noise disappears and lines straighten up, which means that the brain relearns kind of the map of the images on retina and rectifies or reinterprets what is signal, what is noise, and how to it is should be remapped on the real space. So there is some of this neuroplasticity in a matter of months. If you ask about how the overall timeline looks like, so right after surgery, patients left for recovery after subretinal implantation for I think a month or maybe two even until the silicone oil is removed or gas exchange occurs, and after that they are fitted with augmented reality glasses to optimize position of the screen with their interpupillary distance, and they start learning how to use augmented reality glasses, which is like Google Glass. So for some of us who used to augmented reality glasses, it's pretty intuitive, but for people who never use them, it takes time to get used to that. But after that, they get trained to, see first simple patterns and letters and text, and yeah, and they show very good results. So it takes time, but it's certainly is doable in a matter of months. In the next generations, by the way, we'll make our glasses look much more natural, but also will have internet compatibility, so they can actually do all the training at home without visiting clinics. They can, play games and perform various tasks without leaving their home, which will make it much faster and easier.
And just to be clear for people who are watching this, um, this implant is really for people who've already lost a significant amount of central vision. So when this device is implanted, it's not compromising any remaining vision.
Right.
It's just restoring an area of vision that was lost already. Is that correct?
Yeah, that's correct.
So, so how would you qualify for getting an implant of this nature?
Yeah, so currently our trials were focused on patients with age-related macular degeneration. Here you see a fundus photo of such a patient, which have scotoma, this bright spot where there is no vision and normal retina in the periphery. And our next trials will include different types of retinal degeneration. We'll start with the Stargardt disease, which is has similar appearance, but it affects much younger patients. And then if that is successful, we'll try maybe retinitis pigmentosa as well. But currently, everything that was done was with AMD, and in particular, atrophic form of AMD. Atrophic form means it's a death of photoreceptors in the center of the macula. And company applied for CE mark, so if successful, it will get approval in Europe. With FDA, there are discussions of how to proceed, but no submission yet.
Okay, so just so everybody understands, this device is not available for
Yeah,
public consumption yet. We're still
yeah,
waiting for the FDA approval.
right.
Um, so you referred to the fact that it's being put into people in trials with advanced dry macular degeneration. Can it be put into somebody with wet macular degeneration?
Currently, we didn't because wet macular degeneration can be maintained or vision can be maintained by intraocular injections of anti-VEGF molecules and Mm, so currently, this was exclusion criteria. If the AMD is wet, we did not implant. But in principle, if it's wet to such and the retina is damaged to such extent that the acuity is very low and photoreceptors are lost in the area of bleeding, then maybe in the future it will be the indication will be extended. I don't know. At the moment, it is dry advanced AMD.
So, coming from my layman's perspective, the fact that there might be some fluid or blood gathered back there, that's not going to compromise the effectiveness of this device because it's
No, it
possible.
may. It actually may because the blood and maybe debris of photoreceptors create separation between the implant and the bipolar cells, and that separation attenuates the electric field and reduces resolution. So this is important factor. We didn't study, this effect quantitatively in wet AMD, but we do study it in dry AMD, and this is important factor in patients where this debris layer separating implant from the bipolar cells is thin, the percepts, we expect them to be brighter and resolution to be higher.
Well, let's say that the Prima is approved and people have this device put in them, and then a few years go by and you've developed an even better version of Prima.
Right.
Um, will existing versions of Prima be able to be fine-tuned to reproduce this new higher quality vision, or can people have a new implant put in?
Yeah,
With,
so there are two aspects of improvement, or three. We can make better glasses or better software, and that's external, and can be easily, substituted, replaced. Uh, or we can improve the implant, which actually we did already. We have another version that works in rats, but it is not yet converted into a human version. So we demonstrated recently and published that you can replace in rats first generation implant with a more advanced beta implant, and we received the same stimulation thresholds and much better acuity with new implant in the same animal. So in principle, you can swap an implant because it's just sitting under the retina and you can slide it out and put another one in. Whether we'll do it in humans or not, I don't know. It is not my decision because, surgeons are very hesitant with second surgery and so on. I don't want to make those decisions. I'm not MD myself, just PhD. So that decision will be left for the future medical decision, but it's possible to do. We did this in rats.
all right. So we received a lot of questions already from people that received the invitation. I have a number of them here. Um,
And also, Matthew, we've got questions. We've got 7 questions waiting in the Q&A here as well.
okay.
Are you able
So
to see that? I can read them to you, or
Should I stop sharing the screen? So,
yeah, you can.
okay. All right.
okay. So let's see. The first question um, is are there some ongoing clinical trials? Are there slots in those clinical trials that people can get
Yeah,
in and try this?
right. So a company that acquired our French startup called Science Corporation, now a US company, they opened a registry. So anybody who is interested can go to Science Corp website and find in the menu patients section and register for upcoming clinical trials. Um, Currently, there is a plan to do a feasibility trial in Stargardt patients. And also in existing patients, we'll study contrast sensitivity and image enhancement for face recognition. So these are the immediate plans for further clinical trials. As to beyond that, study for FDA approval or study for maybe other forms of retinal degeneration, I don't know the timeline.
Okay. So my next question is probably not answerable at this point, but do you have any sense of when Prima might be available in the US? And also part of that same question that someone asked is, where would this procedure take place?
So currently, the procedure that described in this paper that you mentioned in the New England Journal of Medicine, this implantations took place in 17 hospitals in 5 European countries. So a lot of people participated. In US, there is one hospital where 2 patients were implanted, and then they were not included in the study because of COVID and kind of the trial was left unfinished, and that was in Pittsburgh. But that study in Pittsburgh, or patients were supposed to be recruited 5, but because of COVID, it was kind of didn't continue beyond the first 2. Everything else was done in Europe.
Okay. Um, are there, what are some of the limitations or the restrictions that would disqualify you from getting this implant? We have people asking similar questions.
Well, first of all, I think the visual acuity should be really low for this implant to help, and therefore there is exclusion criteria of the visual acuity. I think it is about 20/400 and lower. If your acuity is better, maybe I'm mistaken, maybe a little better than that, but not much. And then it is disqualifying factor. When our implant will increase resolution, next generation, this criterion will be reduced, and but currently that's a limitation. Also, what is excluded, other ocular diseases. If there are concurrent other diseases, then these patients are excluded. And out of 2 eyes, we implant in a worse seeing eye.
Okay. Here's another question we just got. Would this implant help people with glaucoma?
No, this is not going to help people with glaucoma, because in that case, ganglion cells are being damaged, and if there are no cells left to stimulate, then there is no way to restore vision.
Okay.
So currently, it's only for patients with lost photoreceptors, but other cells remaining in place.
Here's another question that my father would have probably asked because he suffered from macular degeneration and he was an avid tennis player. Can this device improve depth perception uh, needed for sports like tennis?
Currently, it's implanted in one eye, and therefore it will not provide depth perception, because the depth perception comes from binocular vision, and that is not going to improve. If in the future there will be high resolution implants in both eyes, and maybe, but currently it is mostly for reading, writing, and not for improving tennis game.
But if let's say you had this implanted in one eye, it's
Yeah.
not going to decrease your depth perception.
No, it's not going to decrease. It only adds, but it's not adding stereoscopic vision and depth perception at the moment. Another funny fact, by the way, with prosthetic vision, that because we skip phototransduction and photoreceptors, we go directly to second layer of cells. It actually works faster than normal vision. So if in the future, these implants will be high resolution, they may provide an advantage for ping pong players.
Okay. Someone just asked, can you explain the implant procedure again? Maybe we don't have to go into total detail, but maybe more of what the surgery
Yeah,
is.
so what surgery is about is it begins with the injection of fluid under the retina. So retina is elevated, is what is called bleb. Liquid is injected, retina is elevated. Then there is a cut made with a width of about 2 millimeters, which is the width of current implant. And the implant then inserted under the retina through this cut, and retina is reattached. That's pretty much the surgery. So
Okay.
implant is left under the retina.
Is it similar to any other current surgeries?
It is similar in a sense to all the subretinal surgeries that were done in the past for removal of subretinal membranes. Currently, these surgeries are less common because anti-VEGF drugs, treat subretinal neovascularization. But in principle, the subretinal surgeries are all done same way. You inject fluid, lift the retina. If you need to produce a cut, what is called retinotomy, to get into that space, you make this cut. And then we have injectors that delivers this image directly into that opening in subretinal space, and then retina is reattached using perfluorocarbon. It's a heavy fluid, which is then exchanged with either silicone oil or gas. So all of these steps are pretty standard.
A couple more questions. Um, sometimes when there's an incision made in the cornea, it may or may not heal completely. Are there any potential problems? This is not the cornea, it's behind the cornea? Where
Oh,
is
yeah.
it?
No, we are talking about retinal implant, right? So the
Right.
incisions is made several millimeters behind the limbus,
Okay.
behind the cornea. You get into the vitreous space, you remove the vitreous, it's called vitrectomy. So the jelly kind of body called vitreous is removed. And then retina can be elevated, implant can be inserted, and retina reattached. So yeah, I forgot to mention that the vitrectomy is the first step, the removal of the vitreous.
And then over a period of time, the eye replaces the vitreous gel with another substance to
Yeah,
occupy.
but not gel anymore. It will be fluid.
It would be fluid.
But vitrectomy is pretty common procedure on its own. So that procedure is very well established.
Someone wants to know, will having had cataract surgery already prevent somebody from having this
No,
implant?
no, no. Cataract surgery is perfectly compatible.
Oh, okay. Um, I must say the most frequently asked question we got was, do you know if Medicare or insurance is going to cover this?
That I don't know. I can tell you that with Argus 2, which was much worse implant in terms of performance, only 60 electrodes and only light sensitivity, I think the reimbursement was established. So I expect that for our implant, it also will be established.
Well, that's really interesting. Okay. Um, a lot of people are still asking about if you have both wet and dry, would you qualify?
Yeah, if the eye that will be treated, implanted is dry AMD, then yes, I think the other eye can have wet.
Okay. Um,
But again, I am not MD. I don't want to take, responsibility for medical advice. You should ask physician, that treats you, retina specialist, all those questions. And again, register for the upcoming studies in Science Corporation website registry.
okay.
And I put the link to that in the chat. So if people are interested, check the chat. You'll see the link there.
Thank you very much.
And someone wants to know, can you see colors? You already described that it's black and white,
Right.
but what's preventing someone from
Yeah,
seeing
the
colors?
color vision is very, complex. To achieve color vision in normal retina, the signals from two cones of different colors are fed in opposite way to the same bipolar cell. So it's antagonistic kind of inputs, positive and negative. And the difference between two color channels, so to say red and green or blue and combination of red and green, which is yellow, the difference between them is what is actual signal is into bipolar cells. So to reproduce that, we need not only single cell selectivity and stimulation, but also antagonistic input from two different pixels of different colors. And we don't have this technology yet. We are thinking about it. We are working on interface with single cell resolution, but there is nothing practical yet.
Okay. Um, People are obviously eager to have this thing available to them. Um, I guess we'll just have to wait and see. What would the next sort of signal be to the public that availability is coming closer?
There will be probably notifications publicly about submission to FDA approval. There will be probably announcement when it's approved in Europe. I expect that companies, will put this on their website, will be advertised. But again, I am not involved directly in these medical decisions. I develop the technology itself. I study how it works in animals. And so everything I know about clinical results is a one step remote from me.
Okay. Well, here's another quick question. This will be our last question. Can this help with driving, or do you imagine that someday it can be helpful with driving?
I hope that we will get resolution that will help with driving, but the next generation implant will have acuity of 20/80 if everything goes well. And that by itself is not sufficient for driving because in California, at least, you need to have 20/40. And that can be achieved only with zoom function, which I don't think it will be allowed for driving. But 20/80, I think, is already pretty good. I think if I will take my glasses off, that's probably what I have. So, and I drive without glasses. So I think it certainly is improvement compared to what patients have without this.
Okay. Well, thank you very much. We have to respect your time. I know you have to get somewhere else. There are some other outstanding questions. We will do our best to get answers for them, and then we'll somehow communicate that back to the attendees here. So thank you, Daniel, for helping us.
Thank you. Thank you
And
for your interest. And if you have any questions, let me know.
we shall. And thanks to all of you who participated today. You're becoming part of a really engaged community of people affected by vision loss, and we're going to be hosting more of these types of programs on developments that are important to you. And we hope that you'll spread the word that they're available. And as one final reminder, today's program will be available on our website, macular.org, and also on the AMDF YouTube channel. Thank you, and thank you again to Daniel. See you all soon.
Goodbye. Thank you.